So hopefully, this microphone is working. So yeah, super excited to be here. I must say that this is in fact the coldest place I have ever been to. And I know it's like this warm 12 degrees, and by the time I head to the airport tomorrow, it will be -5, I think. So this is sort of an overview of the microservice architecture kind of presentation. So what I'm going to do is really define the microservice architecture and show it's an example of an architectural style. Explain what an architectural style is and what it means and actually why it matters. But before I do that, just a little bit about me. So I actually grew up in England. This is not England, but I thought I have a picture of blue sky and sunshine. I got my start in programming back in the mid to late 80s, building Lisp systems. Lisp, of course, being a functional and then object-oriented language. And in fact, the last time I was here in Minneapolis was for AAAI back in 1988. I think that was when the conference was. So I did Lisp for a number of years, worked on everything like compilers, runtimes, all the way up to tooling and so on and so forth. Eventually ended up programming in Java, and then my book, Pojos in Action, came out, and that was like, gosh, 12 years ago now. And that was about how to build applications with Spring and Hibernate, which back then were revolutionizing enterprise Java development. Gosh, it seems like a lifetime ago. And then back in 2007, I started tinkering around with this obscure service from an online bookstore known as EC2. And when I learned about it, it just blew my mind so much that I ended up creating the original Cloud Foundry. So that was a Java PaaS for AWS, where you handed over your WAR file and it launched a bunch of virtual machines. And just a point of clarification, this was the original Cloud Foundry. So the only connection with the Cloud Foundry that's known today is simply the name. So don't talk to me about any architecture stuff. In fact, the original Cloud Foundry was a simple monolithic application, which actually led to my interest in this microservice architecture. Anyway, Cloud Foundry was acquired by SpringSource back in 2009, and then VMware, and I was part of Pivotal. And then 4 years ago, I left, and since then, I've pretty much been focused on the microservice architecture. So I do consulting and training. So I've actually been in Minneapolis for 2 days teaching a microservices class. And I also have a startup, and we're building a platform to simplify the development of transactional business applications that use the microservice architecture. And one last thing, I'm desperately trying to finish the final chapter of this book that I'm writing on microservice patterns. So hopefully the first draft of that will be done by the end of the month. But you can get, with that discount code, you can get 40% off. And if you can wait until tomorrow, it's half off at manning.com. So that's me. So let's talk about microservices. So I'm going to sort of take a step back and talk about what we mean by software architecture and why it matters. And then after that, I'm going to kind of talk about the monolithic architecture, what that is exactly, what its pros and cons are, and then why the microservice architecture can help. And then after that, talk about some of the drawbacks of the microservice architecture and kind of briefly describe this pattern language that I've been working on that solves architecture and design problems that you will encounter when using microservices. So let's get going. So, first question to ask is, well, what is this software architecture thing? Why does it matter? Except that, if you call yourself an architect, you get paid a lot more, I suppose. So this is a classic definition of software architecture. So it's a set of structures that you need to reason about a system. So it's kind of like it's this tool to enable you to think and evaluate and make decisions. And it's actually, in this definition, which is slightly abstract, it's a set of software elements, whatever they are, and relations or relationships between those elements, And then the elements and the relations have properties, which obviously could involve things like a name. And you can kind of simplify that to a triple: elements, relations, and properties. Or even more simply, it's just like a bunch of boxes and lines, right? That's kind of at a super high level what architecture is. But, there's obviously a deep meaning. So if you think about, the architecture of this building, it's actually sort of multi-dimensional. So from one perspective, there's the structural aspect, the concrete and steel and whatever else this building is made of, which is useful to the structural engineers. But if you're the electrical engineer, then you're interested in the electrical architecture. And then if you're into plumbing, pipes and tubes and all of that, then that's an entirely separate architecture. So in order to properly describe the architecture of this building, you kind of need multiple blueprints, each describing what matters to a particular set of stakeholders. And software architecture is pretty much the same way. In order to properly describe the architecture of a software system, you have to describe it from multiple perspectives, and you have this concept, this notion of views. And each view is a particular set of elements, relations, which then have properties. So this is kind of the classic definition. And later on, I'll explain why this matters and how it relates to microservices. So the classic kind of way of describing software architecture is the 4+1 view model, which was, I think, invented back in the 90s, and then I hadn't really heard about it for years. It just sort of faded away. People seem more interested in the latest JavaScript framework and sort of architecture and stuff like that. So in this view model, there's actually 4 views, so it's capturing 4 different perspectives. And then there's the +1 are the scenarios which are used, which basically, a scenario is how the elements within a particular view collaborate in order to handle a request. So you have the logical view, so which describes what we as software developers create. So since we're programming in object-oriented languages, the logical view is basically classes. Classes are organized into packages. And then the relations are the relationships between those classes, associations, inheritance, all of the standard kind of OO type of relationships, plus dependencies between packages. So that's the logical view. Then you have the implementation view, which is, in a sense, what comes out of the compiler, out of the build system. So that would be, in a Java, it would be jar files, so those are the modules. And then there are the components that are the executables, so they're collections of modules somehow assembled together and turned into executables. And the reason this matters is from, later on you're going to see that the definition of a monolithic architecture is really a system that's comprised of a single executable, whereas a microservice architecture is comprised of multiple executables in a sort of loose sense of the word. Because obviously in Java you don't have executables per se, you typically have war files or something like that. So that's the logical view, what programmers create. Implementation view, what comes out of the build system. Then you have the process view that shows those running components from the implementation view, at runtime as typically a set of processes. So that would be, in a Java application, that would be Tomcats. You'd have a database process. And the relationships within this view represent inter-process communication. And then finally, you've got the deployment view that basically maps those processes onto, quote, machines, which, say typically, well, these days it's virtual machines, could be Docker containers, et cetera. And then the relationships within this view are really just sort of networking, subnets and the like. So those are the 4 views. And then finally, you have the scenarios, which animate this whole architecture. And so in this example, this is a UML sequence diagram just showing how the elements within a logical view collaborate to handle a request. So this is kind of, a good way of describing the architecture of your system, as a collection of views. So if you're writing an architecture document, you can structure it in this way. If you're creating an architectural presentation, you can structure it this way. It's actually quite remarkable. This, I've worked with various clients over the past couple of years, and actually encouraging them to use this structure has actually helped how they communicate their software architecture. But that's sort of kind of a whole separate topic. So we've got this notion of architecture, we've got this notion of views to describe it, and then there's this concept of an architectural style. And that really is sort of a set of constraints on the palette of components that you have to build your architecture, and how they can and then how they can be structured. So the classic example of an architectural style is a layered architecture, where you have a set of components or elements of some kind, and they are organized into layers, where each layer has a well-defined set of responsibilities, plus there are constraints on the dependencies between those layers. If you have strict layering, a layer can only depend on the layer that's immediately below it. If you have more relaxed layering, then it can depend on any of the layers below it. But it imposes constraints on the structure of your system. And that ties back into the microservice architecture, because that is actually an architectural style. So anyway, blah, 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 architecture, why does any of this matter? And, at some level, if all you're concerned about is just cranking out code and implementing version 1 of your product, maybe not so much, right? Because you can take any sort of, if you think about requirements, they're really divided into two types. You've got the functional requirements, the use cases or user stories that describe what the system does. And you can implement, basically any set of requirements with roughly any architecture. At least it will sort of function in some way. And then but then there's also the non-functional requirements, or the ilities. And in order to achieve a particular set of ilities, that's when you need to explicitly think about architecture. And if you think about you're working on some incredibly large legacy system and development is slow, that's probably because not enough thought has been given to the architecture over the years. So if you go to wikipedia.com, there's actually a page on listing these ilities or non-functional requirements, and there's a lot of different ones. Obviously there's important ilities are things like scalability. Reliability is also another really important attribute. Can determine whether your site is up or down. It was really funny. I went there on Sunday to grab the logo to stick on the front page of my slides. So it was I was amused to see that the university site was down. So it's not strictly an architectural thing, but it's good humor, right? But the thing that really, the three attributes on this that I'm particularly interested in are the top three. Maintainability, testability, and deployability, because those are the ilities that directly impact your development velocity. And today, obviously all of the other ones are quite important, but today the speed at which we can deliver software, reliable working software is becoming increasingly important. Businesses are sort of under increasing pressure to just innovate and do all that digital transformation stuff and building systems of engagement with their customers and so on and so forth. And what that means for us as developers is we need to build better software faster. And sort of the pace is picking up and accelerating. Companies are terrified that some fast-moving Silicon Valley company that's intent on changing the world and disrupting things will actually disrupt their business and so on. So we need to do a much better job at delivering software. And a big part of that, we just need to accelerate software development. And there's actually two key attributes that we need to focus on. One is reducing the lead time, reducing the time from when a developer commits a change to that change going into production. Hint, it should be, should not be 3 months. And also increasing the deployment frequency, the rate at which we're doing deployments. We need to dramatically improve those metrics. And in fact, if you go look at sort of what is the state of the art today, the numbers are quite astounding. So this slide is actually from the DevOps report that's published every year, and it surveys organizations, asks a whole bunch of really interesting questions about their development practices and so on. And then, but some of the metrics are just absolutely astounding. So, if you look at high-performing IT organizations, they're deploying into production many times a day. One of the most shocking statistics is Amazon, because I think, was it back in 2014, they were deploying into production every 11.6 seconds. So that's something to think about if you're still deploying every 3 months, for instance. Also, the lead time in a high-performing IT organization is really short as well. Under an hour. Netflix have a story about how a developer was able to commit a change, and then within 15 minutes, that change was deployed into production. So these companies are moving extremely quickly. But not only that, they're actually deploying software in a much safer, more reliable way. So the number of bad deployments is significantly less. And if there is a bad deployment, the time to recover from that bad deployment is also significantly less. So they're actually moving fast and not breaking things, as opposed to sort of the more traditional, we have to be careful, we have to release every 3 months and make sure that it's working before we push it into production. And then when we do, it means you have 50 people working through the night. Whereas these organizations are just constantly deploying during the day. Though it does turn out that companies like Amazon, they don't tend to deploy software between Thanksgiving and the New Year. Which is kind of interesting. But anyway, so it's all about moving fast and not breaking things. And the way you do that really is a combination of 3 different things. You have to have the right process, which is basically DevOps. And a part of DevOps is continuous delivery and deployment. You have to have the right organization, which is really having engineering consisting of small autonomous teams. And then you also have to have the right architecture that gives you the ilities that enable you to do DevOps. And so then the question is well, what is the right architecture? So I'm going to talk a little bit about that. And if you think about kind of, in a sense, the de facto architecture that we've used for our systems has really been this monolithic architecture. And then it's like, well, what does that mean exactly? So if you look at a typical application, from a logical view, it's actually quite sort of modular. It's comprised of layers, and it's comprised of packages. There are sort of packages implementing various different business functions, like on an online store, catalog management, recommendations, reviews, and orders, and so on and so forth. So we've kind of got this nice structure, at least in an idealized application. But then when it's sort of time to deploy it, what we end up doing is packaging the entire system up as a single executable component. So from in the implementation view of the architecture, there's just one component. And so that's sort of the definite, like in Java, that would be a WAR file, and you'd probably run a set of, your application is a set of tomcats that's clustered. So, sort of the definition of the monolithic architecture is that it's an architectural style that structures the application as a single executable component. So there's a slight variation of that where you actually have a set of executables, but they use a shared database, and they basically have to be deployed in lockstep. So even though there's multiple pieces, they're really just one thing. But this is not necessarily bad, because if you've got a small-ish, monolithic application, you can still develop and deploy it quickly. It has good maintainability, testability, and deployability. The problem that you have is successful applications have a habit of growing. So in the beginning, it's small. You got a small team, small application, high development velocity. But the application will just get bigger and bigger over time. This notion of maintenance is sort of doesn't really mean anything anymore. Where just development does not stop. And if you're more successful, you have more money, so you hire more developers. And so the pace of development picks up, and your application is just getting bigger and bigger and bigger, and the team is growing. And maybe you try and split the team into sub-teams, but they're all contributing to the same code base. And at some point, you're going to end up with an incredibly large application. For instance, one client I visited recently, their application, the war file, was 1.2 gigabytes of development, of code, right? That's 10 years of development. Another client I visited, I think they had like 1.5 million lines of code, 750,000 lines of stored procedure, 750,000 lines of Java code. And that was the result of 10 years of steady development. And the problem you have is when you have something that large, any notion of sort of agility is just, it's impossible, right? But you're basically in what I call monolithic hell. It's not 100% guaranteed that you will be in monolithic hell, but it is extremely likely, because along the way, the architecture of the modularity of your system is likely to have decayed. The system is too complex for any developer to keep in their head, and so the rot sets in, and you end up, to quote a big ball of mud paper, a squalid, sprawling slum of code. And then not only that, the technology, you're very likely to be stuck with the technology stack that you started with, simply because it's not feasible to rewrite it to use something more modern. So you've got this code base that's a squalid, sprawling slum written using some ancient technology that you have difficulty hiring people to develop. So basically, you're sort of in this world of pain, and the ilities of your architecture are not good. It's not maintainable, it's not testable, and it's not deployable. So that's sort of the kind of the motivation for this microservice architecture. And so the idea, of course, is that, well, we just, instead of building one big thing, we just split it up. So into smaller things that are easier to develop and test. And so that is in essence, that is the microservice architecture. So you can define it as an architectural style that's in the implementation view that structures the application as a set of executables or services. And those services are loosely coupled, and they're organized around business capabilities. So each service in your architecture implements a particular business function. So the notion of business capability is a little abstract. The strict definition of it comes from business architecture, but it's really something that a business does to deliver value. So if it's an online store, you've got order taking, inventory management, delivery management, and so on. In a purely manual business, you would have people or groups performing those functions, and that's your business architecture. So with this, sort of a lot of software development is automating what businesses do. So you kind of take your business architecture and transform it into a corresponding set of services. So for an online store, there would be an order service, there would be a catalog service, an inventory management service, and sort of so on and so forth. So you could sort of show your architecture to a business person, and they would be able to make sense of it at a high level at least. Then in terms of, well, what is a service? So it really is this independently deployable component. And so obviously it's implementing some business rules in general. Each service actually has its own database. That's important from a loose coupling perspective, and I'll talk a little bit about that more in a minute. And then in terms of, how does it interact with with kind of the rest of the system? So from a kind of this sort of two halves to the service, there's the consumer-facing part, and then there's sort of the implementation part. The consumer-facing part of a service has an API that, enables its functions to be invoked by its clients. So it will support commands, the creates and the updates, and it will support queries. And that API can use a variety of inter-process communication mechanisms. It might use a synchronous mechanism like REST or gRPC, or it might use some asynchronous communication mechanism, might listen to messages on command messages on a message broker. The service might also publish events. I think Randy's going to talk about this later in the day. You're going to see that in a microservice architecture, it's extremely common for services to publish events, specifically domain events, when their data changes. And that's sort of all part of the public interface of a service. And then there's kind of the implementation of a service. A service might invoke other services. So it's kind of the mirror of its inbound interface. It might make REST calls to other services. It might send messages to other services. And then it will also potentially subscribe to events that are being emitted by other services. Whereas in particular, it's quite common in a microservice architecture for a service to, in its database, it's going to have objects that it owns. So the delivery service will own delivery entities, but it might also contain replicas of data that other services own, and that those replicas are maintained by subscribing to these change events. So that's kind of just, give a sort of precise definition of what a service is. It's one of these independently deployable things with a bunch of APIs. So I haven't really talked about the size of a service because I don't think that matters too much, or at least don't take the phrase micro or the word microservice in a literal sense. In a way, that's a terrible term because it makes, you look in the literature, people have talked about services with 100 lines of code, which is just plain silly, 2 weeks of work, so on and so forth. Really, this is a service-oriented architecture, except that SOA has just such terrible connotations that you can't call anything that, right? From a marketing perspective, it was necessary to give it a new name. But really, from my perspective, the essential characteristics of a service, so sort of earlier I described kind of the technical side of it, but really it's something that implements meaningful business functionality, and it's developed by a small team. So it's sort of, if you turn it around and you think, well, we have to organize development by structuring engineering as small teams, then what's the architecture? Well, the idea is each team owns one or more services that they can deliver with minimal lead time and high deployment frequency. And provided the service kind of meets that definition, it doesn't exactly matter how large it is. So, if you have 30 people working on a service, that's probably too big. The team should probably be split into, well, at least in half, possibly into thirds, and the code base should be split as well, assuming that they're not actually able to deliver quickly. But in general, you want to have small teams, the so-called two pizza teams, working on these services. So that's what I'm going to say about size. So then kind of coming back to the sort of the title of this talk, So from my perspective, the term microservices is really a linguistic shorthand for microservice architecture. It's very convenient to say microservices, and sometimes it's useful to say microservice, except really what you're talking about is an application architecture. And so in a sense, it's not really useful to think about services in isolation. There's really a set of collaborating services. And part of the motivation for the talk was, you see, like occasionally I'll see a tweet and it's like company XYZ is offering a microservice for something, which is like, you cannot offer a microservice. You can offer an API, but you can't offer a microservice. It's really an application architecture thing. So going back to the online store, you'll have an architecture that looks like this. So you have a bunch of services. Each service has its own database in order to ensure loose coupling, which creates all kinds of interesting challenges around data management, around maintaining data consistency, and around querying. In a sense, that's the biggest challenge with the microservice architecture. Things like deployment, Kubernetes, Docker, those are sort of actually secondary issues to dealing with data in a microservice architecture. You can also functionally decompose the server-side presentation tier as well, so you can have web applications that implement the pages for certain functional areas of your UI, product browsing, product details, checkout, and so on. If you're exposing an API to the outside world, mobile devices or JavaScript running in the browser, you typically put an API gateway, which basically is a facade in front of your services and exposes APIs to the outside world, so like REST APIs or whatever. And you might also have inbound gateways, so you could imagine in this system, suppliers are sending in messages, so they go via an inbound gateway to the catalog service. So interesting thing about this is that, well, there's many more moving pieces, which kind of hints at one of the drawbacks of the microservice architecture, namely its inherent complexity. It's a distributed system with lots of moving parts. It's not a free lunch. But what's interesting is about when it comes to the individual services, they're much more maintainable, much more easy to test, and they're much easier to deploy. You can deploy each service independently as opposed to having to deploy the entire system in lockstep. So, so why does this matter? So in a sense, the real motivation for the microservice architecture is not just, it's not an end in itself. It really is a means to the end. And the ultimate goal is really the rapid, safe delivery of complex software applications. Or to put it another way, microservices enables you to do DevOps of large, complex applications. And it enables that in a couple of different ways. First, the microservice architecture gives you the testability and the deployability that DevOps actually requires. It's kind of two, in a sense, DevOps and continuous delivery relies extremely heavily on automated testing. And so you have to have a testable architecture. If you've got a large monolithic architecture, which in itself might be really, really difficult to test, or if you have, you do have extensive automated tests for it, they might take days to run just simply because of the size of the application. That's not giving you the testability that you need. Whereas these services are small. You can test them quickly. And then also, they're independently deployable. So you have the deployability that's required. And then also, as I've mentioned, this architecture supports these small autonomous teams. Teams own their own services and work on those rather than having to contribute code to a giant code base, which requires a lot of communication and coordination to get changes into production. So that's kind of the essential benefit of using the microservice architecture. But another benefit is the microservice architecture lets you evolve your technology stack. You're no longer constrained to use the same technology stack for your entire system. So when you create a new service, at that point, you can pick a new technology stack. For instance, you could experiment. Like you've heard that, well, Golang is cool, right? Because Google uses it. And so you go off and implement a service in Golang. And then you discover that it's really nothing better than C with garbage collection. Oh, don't get me started on that. Why you have a language that doesn't have exceptions, it just boggles the mind, really. Yes, I love to check my return codes everywhere. No, I mean, to be honest, there's a set of trade-offs. But, if you're like me, you will realize that Golang is way too low level for building your modern enterprise application. I'm sure it's good for something. But that in itself is not a disaster because you haven't invested 2 years and 100 person, or hundreds of person years building a language and a technology stack that you realize you don't like anymore, right? It's a relatively small development effort. Yes, you have a service written in a technology stack that you don't like, but hey, later on when it's time to make major changes to it, you can rewrite it to use something higher level, like Java, or Kotlin, or Scala, anything higher up sort of the evolution stack. So it sort of lets you experiment and safely, but it also, more seriously, it does let you sort of kind of evolve your technology stack incrementally over time. So it's generally a good thing. But, the microservice architecture, has some significant drawbacks as well. As Fred Brooks once said back in 1985, he's the author of the Mythical Man Month, there's no such thing as a silver bullet. Every technology has drawbacks. Unfortunately, we tend to just focus on the benefits when discussing things, but in reality, there are always drawbacks. And so in particular, with the microservice architecture, the biggest drawback is really the complexity of your system. It's really interesting. So you actually break up your system, and you make the individual pieces smaller, which is great because your life as a developer is generally a lot easier. But on the other hand, there's the complexity of the pieces having to fit together. So you're building a distributed system, so there's development complexity of dealing with inter-process communication, partial failure, managing distributed data. There's actually testing complexity as well. The services are really easy to test in isolation, but then making sure that services can actually collaborate successfully, that someone, for instance, hasn't changed an API in a breaking way, is challenging. Fortunately, there are good testing patterns for that, like consumer contract testing, but it's something else that you have to think about. We should, by the way, always try and avoid doing end-to-end testing because those types of tests are brittle, complex, and slow. Ideally, you want to just test services in isolation and then put them into production and finish your testing there. It's not as casual as it sounds, but basically you can do things like you deploy version 2 of a service, and then you arrange for only your test users to have their traffic routed to that, to that service. So it's, in a sense, you're testing in production, but it's in a very disciplined way. From a deployment perspective, operationally, there are many more moving parts, right? Before, you had one monolith and you just ran a whole bunch of copies of it. Now you have tens or hundreds of services, each one of which will have multiple instances. So there's just many more moving parts to manage and monitor in production. The good news is that there are, the deployment frameworks that we have available today are quite sophisticated. Sort of the revolution of that kind of started with you say EC2, 10 plus years ago, right? But now it's continued, and now we have Docker, and we've got higher level frameworks like Kubernetes that provide a very high level of automation. And then there's also Cloud Foundry as well, and other PaaSes like that. So the good news is that, yeah, there's a bunch of complexities, and some of it you just, as a developer, well, we just got to use the right frameworks, we got to use the right testing patterns, and we have to, from an operational point of view, there's tooling to help. And for the most part, it's sort of moving complexity from, having a giant code base that overwhelms our brains to things, to an area that can be automated away, or at least we have a lot of good tool support. So you can't eliminate complexity to some extent. You're moving it around, but you're moving it to a place where tooling can help with that. But it's not for every application. So sort of a key question is, well, is it a good fit for my application? And also, is it a good fit for my organization? Is there a sufficient level of, say, organizational maturity that could actually support developing microservices successfully? Have you fully committed to automated testing? It's actually quite remarkable. There was a Source Labs report that said only 23% of organizations were extensively using automated testing. And many were still relying on a lot of manual testing. If you want to develop software quickly, you have to use automated testing. And trying to skip over that and just leap to microservices will just end in tears. It will not go well because the microservice architecture really does require you to do automated testing. So it's like, as part of any migration to microservices, you really, really have to commit to embracing modern development practices like automated testing. And in reality, along with DevOps, all the other DevOps practices as well. And at some point, once your system gets to a certain level of sophistication, you are going to need fully automated provisioning as well. So it can be a big change. You're reorganizing into cross-functional teams. The VP of the QA organization won't be happy because his organization will not exist anymore, right? Or at least will change quite a bit. Teams will have testing capabilities as part of them. And also once you adopt the microservice architecture, there are all these issues, sort of architecture and design issues that you have to address. And there will be a test on this slide later. So there's a bunch of complexity and issues, and it kind of depends whether things are whether it's a good fit, and then how do you apply it. And so to help with that, I created the microservice architecture pattern language. So that's a collection of patterns that solve various architectural design, development, and operational problems that you will face when using the microservice architecture. I think it's interesting. It's very much work in progress. When I first created it, there were like 3 patterns: microservice architecture, monolithic architecture, and API gateway. And it's gradually evolved over time. Every so often, I add more patterns. So first question to ask is, well, what is a pattern? It's kind of been an old idea in the software community since the mid-90s. So a pattern is a reusable solution to a problem that occurs in a particular context, which is great because it says, in one context you'll solve the problem one way, but in a different context you might solve the problem differently. And patterns were, of course, popularized by the design patterns book, the Gang of Four book, which was a collection of object-oriented design patterns. But in general, patterns are much more sort of general purpose than that. You know, a couple of months ago, I was at the Patterns Conference. It was like the 24th Patterns Conference. And the group that I was in had people who were designing online training, and they had patterns for designing effective online training. So it's sort of, you know, patterns are applicable to many different domains. And a lot of the value from patterns comes from the fact that they're a very sort of objective way of representing kind of design choices or technologies or design decisions. You know, so patterns, you know, they have a name. The pattern has to describe the context. In other words, the situation within which you're trying to solve a problem. A pattern also has to describe the forces. These are the various issues that you have to address or consider when you're trying to solve this particular problem. So, you know, like with a microservice architecture, the context is, oh, we've got this large complex software system. You know, forces include, well, we need to be able to develop quickly, we need to be able to test easily and deploy frequently. You know, the problem is, well, what's our architecture? And one possible solution, of course, is the microservice architecture. So that's pretty good. So it's saying, well, we're trying to solve a problem within a particular context, and here's the solution for it. But really the power of patterns and the reason why patterns force objectivity is because of this, the next two sections, namely the resulting context. And the resulting context describes the benefits, which is sort of what we always tend to talk about, right? Such and such is awesome, it rocks, and so on and so forth. But when you're describing something as a pattern, you have to describe the drawbacks as well. You know, what are the problems with this approach? So one of the drawbacks of the microservice architecture is the inherent complexity of it. And then you also have to describe the issues that you need to resolve when you apply this particular solution. So in the terms of the microservice architecture, there's dozens of issues that you have to address around inter-process communication, distributed data management, deployment, testing, monitoring, and so on. So the beauty of expressing this as a pattern is that it makes all of these issues explicit rather than you trying to just sort of going, yeah, microservices are awesome, and you now have to, and then you later on figure out what the problems are. So, you know, so when knowledge is expressed as a pattern, it makes it explicit the various issues that you will now have to consider. And then not only that, a pattern also has to describe the related patterns, and there's two types of relationship. There are the patterns that provide alternative solutions. So it's like, yeah, you could use the microservice architecture, but maybe you should go consider the monolithic architecture. That has these other trade-offs and might be a better fit in this particular context. And then the related pattern section also has to describe the patterns that solve the issues that are introduced by this pattern. So in other words, a given pattern like the microservice architecture will say, yep, there's a whole bunch of issues. You can solve this issue by applying the Saga pattern, that issue by applying the CQRS pattern. And then there are these various monitoring patterns that you can use in order to be able to troubleshoot problems in this architecture. So it's sort of pointing you in the right direction. And so these patterns end up forming a web or a pattern language. So this is the pattern language. If you go to microservices.io, you'll see a much more readable version of it. And you can even click on the patterns and it's a responsive image and it links, which is really cool because I detest programming in JavaScript. So go check it out. And so in the remaining few minutes, I just kind of want to quickly go through, sort of highlight how this pattern language can guide you in your decision making. So sort of the idea is it sort of, shows you what decisions you have to make, and then for each of those decisions, what the available options are, and what are the trade-offs, the benefits and drawbacks of each of those options. So, you know, at a high level, the first question you have to ask is, well, what the heck is my architecture? Should I use the monolithic architecture, or should I use the microservice architecture? And obviously, there's a bunch of forces around maintainability, testability, and deployability, or so on. And so it's sort of like, well, should I build a system with a single executable, or should I build a system consisting of a set of loosely coupled executables? So that's kind of the high-level decision that you need to make. The next question is, well, if you decide to use the microservice architecture, what should my services be? And there's a collection of various forces, and you know, services should be loosely coupled. They should be small enough that they can be developed by a small team. They should be cohesive. The APIs should be stable, and so on. And so there's patterns that can provide guidance on how to do the decomposition. You can decompose by business capability. So that's sort of applying a business architecture perspective to the decomposition process. Or you can apply domain-driven design concepts of subdomain and bounded context in order to come up with your services. So that's sort of step 2 in the process. And then the next decision is well, how do I maintain data consistency? Because each service has its own database, and sometimes business transactions will need to span multiple services. And it turns out for a variety of reasons, just two-phase commit or distributed transactions are not really an option. And so for that, you're going to end up using sagas, and then there are various different ways of implementing the saga pattern. And actually underlying it is this, as I think you're going to see in Randy's talk later today, underlying all of this is an event-driven architecture. Services are typically publishing events whenever their data changes, which can trigger changes in the other services in order to maintain data consistency. And you also have a problem with querying as well. You know, if you want to find the status of an order, the order status is partially in the order management system, it's partially in the delivery management service, and it's probably in the billing system, and so on and so forth. And it's like, well, how do we gather all of that data together? You can't do a distributed query because the data is private to each service. So there's 2 patterns for that. There's API composition, where you just invoke each service's API and basically join the data together at the application level. That works in some situations. In other situations, you have to use the CQRS pattern and maintain a replica of the data. And you do that. And a service will do that by subscribing to the domain events, the change events that are being published by the services that own the official copy of the data. So once again, events play a quite central role in this. So to a large extent, these are sort of the key issues that you have to deal with. It's all to do with decomposition, data management, and actually transaction management. And interestingly, almost everything else is kind of like a second level of technical detail. So, one client I talked to recently, it's like they wanted to go off and spend hundreds of thousands of dollars buying a deployment platform. And it was sort of like, it might feel good because you're spending money and making a decision. But in reality, your deployment platform is when you don't actually have any services and you haven't really fully understood what the requirements are for your deployment platform anyway, going off and buying it up front is not the best use of your money, right? Go off and build some services and understand what the problems are and do the proper decomposition. And yeah, at some point, make the decision around deployment and so on. It's really, really secondary. But, there are technical issues around, how do services communicate? I mean, some of this actually is slightly important because it ties back in with transactions and so on. But for the most part, sort of whether you use REST or gRPC, you know, it's not that big a deal. You know, you got to pick one and so on. How you manage your APIs is much more important than how you kind of implement them. You also have to pick a framework upon which to build your services, a so-called microservice chassis. You know, if you're using Java and the Spring framework, then Spring Boot and possibly Spring Cloud are the obvious choices. If you're using some other language, there are other sort of microservice chassis frameworks out there that can help. At least most languages have something. Not so sure about PHP and there's some of the older ones. But like Golang, there's GoKit and microservice chassis. And then, at some point, you need to figure out how to do deployment as well. Interestingly, when you're starting to refactor your monolithic monolithic application, and you only have a few services, this is not that important. At some point, it will become important when you have a whole ecosystem. But it's sort of like, you know, it's not a hugely critical decision initially. But, you know, the choices are fairly straightforward these days. You can, you know, Kubernetes or Cloud Foundry, or some hosted Kubernetes on AWS, or possibly, you know, serverless solutions like AWS Lambda are also quite good. I mean, in fact, sort of my kind of decision-making process is like, is it a good fit for AWS Lambda? Deploy it there. Oh, well, okay. If it's not, then I would use some Docker-based framework, and maybe if that's not a good fit, I'd end up using like EC2 instances, Beanstalk or something like that. But so there's sort of there are in fact various trade-offs around these, and so pick the one that involves the least amount of sysadmin work. And then there are sort of other technical issues about like discovery. You know, when one service wants to invoke another, it needs to know the IP address, so you need to implement some dynamic discovery mechanism at some point. Interestingly, you know, the older way of doing that is to sort of handle this at the application level. So Netflix have popularized this with Eureka Service Registry and the add-ons which have been wrapped up by Spring Cloud. The reality is modern deployment frameworks like Kubernetes and the other Docker ones kind of have this built in. So you really should be just leveraging the infrastructure rather than having to handle this at the application level. Monitoring is actually a really important topic. If you have requests bouncing around a whole set of services, troubleshooting is extremely challenging, right? So there are patterns like log aggregation. So centralize the logs in like Elasticsearch or Splunk. Use distributed tracing that assigns every request an external request ID, which then gets included in every log message, so you can search across the logs and see all the related log info, as well as building a graph of the service calls as well, and sort of so on and so forth. So you apply these patterns to provide insight into your application and troubleshoot problems and so on. So anyway, so that's pretty much my talk. So that's sort of how the different ways that you can use the pattern language. So sort of to summarize, you know, the goal of architecture is to really satisfy these non-functional requirements. And today, you know, in addition to the usual non-functional requirements like security and reliability and scalability and so on, you know, speed of development, namely maintainability, testability, and deployability, are becoming really, really important. And it's, you know, effectively you want to use DevOps. And, you know, if you're building a small application, then probably the monolithic architecture is fine, but if you're building a complex application, you're probably going to have to use the microservice architecture. And then you can use this pattern language to decide your decision making. So that's my talk. Hope that you found it useful, and well, thank you for listening.